Hi everybody, this is Dan Sullivan, and this is the first official sort of non-math video on power generation. I just want to make sure that you understand how important that math is. I know it can be a little intimidating, I know it can be a little daunting, but the fact is that all trigonometry is memorizing what the sides of a triangle are called and knowing how to divide their lengths and using that number to figure out angles. It's a very old mathematics. Your great-grandfathers used it for carpentry and masonry and plumbing, and they actually called it trigonometry. Whatever you do, don't sell yourself short. You can do it. I promise you, you can do it. You just got to practice. Okay, so the first topic we have to discuss in power generation is magnetism, okay? And it's usually taught early in the class, an electrical class. It's usually taught as theory, and it's usually taught as sort of something you study and you learn and you take a test and you pass it and then you immediately forget it. Well, that's a really bad thing. I cannot overstress in any way the importance of understanding the basics of magnetism when you want to understand power generation. Magnetism is the key to making it and the key to controlling it. And you have to understand what's actually happening with a magnetic field. You have to understand what magnets do. Nobody really knows why or how they do it, but they do what they do, and we can observe what they do, and we can control what they do, and we can make it, and we can change it, and we can do a lot of things with it, but we can't explain what it is. If anybody tells you they know, they're lying because they don't really know. In fact, if you read the textbooks, it'll say magnetic domains and blah, 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 but it just kind of talks around the topic. It doesn't actually come out and say magnetism is this. We don't know. Okay? So it isn't important that you know what makes something magnetic, but it is critically important that you understand what magnets do and how they do it for mechanical reasons and how to control it and where they are. Magnets are everywhere, okay? Magnets are absolutely everywhere. One of the most obvious things that you've dealt with in your lifetime, more than likely, that involves magnetism is a compass. And a compass is just a little bar magnet that has polarity, north poles and south poles, and those north and south poles are attracted to or repelled by the north and south poles of the planet or another magnet. Okay, so all the compass is a little bar magnet. And I've taught in the past, and maybe you remember, that the compass can be used to test solenoids, because solenoids produce a magnetic field. So there's one device that produces a magnetic field. You can also use compasses to diagnose relays, because relays use a magnetic field. It's electromagnet. We're going to get to that in more detail later. But the compass is, in its purest sense, the simplest magnet there is, okay? And at least for our use. And you notice that I've used the colors, and we have a north pole and a south pole. And if I take this mag pickup again and put it there, then I can, let me see if I can do this right here. There we go. Okay, there we go. Just to, you can see, sorry, I'm probably covering it up. All right, there it is right there. Okay, so move it down here a little bit. Okay, so it's very the concept of magnetism is essential, and you can't make it through EPG without understanding it. Okay, because it's the heart of it. Magnetism is the heart of the generator. fuel is the heart of the engine or the prime mover, or water or whatever is being used to convert potential energy into kinetic energy in order to turn the generator. But inside the generator, magnetism is king, and it's the single most important thing that you can understand. So the first thing you have to understand is that we talk about magnetism in terms of polarity. All right, we have poles, P-O-L-E-S, poles, and those poles are referred to as north and south. All right, and that's primarily because when the first magnet was discovered, it was discovered that it would point north and south, and therefore the folks who figured out north and south and chose the terms north and south because the compass needle pointed north or the compass needle pointed south, depending upon which way you look at it. But at any rate, so you will always use the phrases or the terms, north and south to describe the different poles. Now I can explain to you how to make certain poles, and one of the things I was considering doing here is making a little compass out of a paper clip when I start doing electromagnetism in later videos, but because I've done that before, it's kind of cool. It's an experiment you can do. But you got to remember this: north and south, north and south, north and south. All right, that's very, very important. Okay, and the northness and the southness generally don't matter when we're talking about all of these things. Okay, as a general rule, the northness and the southness don't really matter. And that's just the way it is. It is and it isn't, and it does and it doesn't matter when you start talking about some of these DC devices. Okay, so even though there is a north and a south in here, you and I don't care. All right, this solenoid with its magnetic field coil here, I'm using terms a little ahead of time here, but there's the valve part, right? And there's the coil part right there, and it would have two wires on it, but they broke. So that's just the way it is. I don't know if you can see them, but maybe I can zoom in here. But they had two little wires right there, and we'll get into that later. But anyway, that was the coil part, or is the coil part. And in these devices, the northness and the southness don't really matter. Okay. Now, one exception to that, for our benefit, is the DC motor, because we do control the direction of the DC motor by controlling the polarity of the different fields. Now, this is a permanent magnet DC motor, and that's because it has those little black magnets on the inside, and those don't change, hence the term permanent magnet motor. Now, in generators, you're going to hear the term PMG, and the term PMG means permanent magnet generator. Okay, so permanent magnet generator, you will hear that, and you need to understand that in a PMG there are black, usually very brittle, they're changing a little bit, but PMGs have permanent magnets in them. Okay, so there are two magnetic fields in here. There's only one magnetic field in the relay, but inside the motor there are two. All right, and in the generator there are two magnetic fields that matter. So we're going to eventually talk about that, but for our purposes right now, all of these other things that I showed you do not really have a polarity concern, and it doesn't really matter, but it's there. In the motor, it matters only to the extent that we are going to reverse one of them in order to reverse the direction of the motor. More on that later, because that's a slightly different discussion. However, when we start talking about these things later, this is what is there. Okay, now I can show you what the magnetic field looks like because I drew another picture somewhere. Oh, wait a minute. Yeah, I did. No, I didn't. Wait, okay, hold it. I gotta think what I'm doing here. Oh, I know, okay, okay. Now I remember what I was gonna do. Okay, sorry. All right, okay, so we got the north and we got the south, okay? Now, for whatever reason, I don't know why, but I always think of magnetic flux in my head. That's the word you got to know. Flux field. Flux field, that's important. You got to know that, all right? Because you're going to hear the term field coils, field poles, field circuit, F1, F2, F plus, F minus. Exciter field, main field, field, okay? That's talking about what's happening around the magnet, and that's what the magnet produces. The magnet produces flux, okay? Well, there's a critical understanding to flux that you have to know in order to see what's happening in the generator. And you guys know by now the way I teach is that I want you to see what's happening. I don't want you to just be able to pass a test. Passing a test is stupid and doesn't prove a damn thing. What matters is, can you go out and say, this is how it works and this is what it's doing, and then fix it, okay? Well, I don't have the best angle on this, but I'm going to try. So the way this works is the flux flows out of the North Pole. Just by convention. We don't know what the hell it's doing, okay? We really don't know what's happening there, but because we have to have something to sink our teeth into, we have to have something to understand visually, because we're visual people. Flux flows out of the north, and flux flows in to the south. So it flows out of the north and into the south. That's just the way it is. That's just I have no idea what this is. None. But it's there. I can see it. I can find it. I can feel it. I can measure it. I can use it. And I can do a lot of things with it. I can't tell you what it is. All right? But the key to understanding what's happening here is that that difference in direction makes all the difference in the world in the operation of a genset. All the difference in the world. That into and out of, okay, that into and out of direction, that change of direction, that alternating direction is what makes alternating voltage possible, and alternating voltage produces alternating current. So the fact that there is a North Pole immediately followed by a South Pole, immediately followed by another North Pole, immediately followed by another South Pole, blah, 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 ad nauseum to the end, okay, just running all the time. The fact that we're using an alternating magnetic field to produce an alternating voltage, because generators produce voltage. Generators do not produce current. Generators produce voltage, which then allows the system to demand current. So alternating magnetism produces alternating voltage, which then allows us to create alternating current, alternating amperage. All right? Now, that's the first thing. The second thing is, it looks like this. I'm not doing a great job here because I don't have a very good angle on it, but at any rate, you have to imagine that it's there. What I'm not drawing is the perfection of it. It would be perfect. I mean, it would be perfect. I'm going to show you that in a minute. But it's going to be perfect. Okay? That's what the flux field looks like. You must see that picture in your head when you think of a magnetic field. Anything that's magnetic, it doesn't matter. This produces this. This produces this. This produces this. this produces this. Okay? And this is the business end of the generator right here. This is the business. This is where all the magic happens, right in here. This is what you have to remember, because you remember we were talking about angles in the trig, right? We were talking about angles. Well, look, angle, straight line, 90 degrees. Angle, 90 degrees. Angle. Okay, so there are angles here that we have to deal with. And on the last power generation, on the last trigonometry video, we talked about 90 degrees. Okay, now I'm gonna show you this, but I'm gonna show it to you quickly, and if it sinks in, it does. If it doesn't, you'll at least know I said it, and I can come back to it. But this rotor, which is rotating rotor, inside the stator, which is the stationary windings, if this rotor is rotating, or if this wire is moving, notice that when the wire is here moving in this direction, there's no angular difference. The flux field is flowing this way, the wire's moving this way, they have the same angle, the difference is 0, and if you remember, the sign of 0 was 0. So when the wire is here, there's no magnetic friction, and hence there's no voltage. But then, generators move in circles, right? So now, when it comes around to here, notice it's now moving this way. It's moving this way now. It's turning. It's doing this. La 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 la. Generator. Okay. And then at this particular point, notice that here's this flux line coming straight out. It's over here too. And then it's going la 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 la. Now notice right here, 90 degrees. So when these flux lines are cutting across this wire right here, the wire's in this direction. I know it seems stupid right now, but trust me, okay, there it is. When it's all turning, when that line of flux is 90 degrees relative to the motion of that wire, or whichever, doesn't matter which one's moving, as long as they're moving. It's called relative motion. This is where maximum voltage is produced. And then it comes back around here, and now the angles are 0, so there's no voltage being produced. And now it's coming around here, and now there's maximum voltage being produced. But notice it's moving in the opposite direction. Okay, so we end up with an AC magnetic field. But it's all because of that flux. This is the mechanical picture. You, as a mechanic who looks at mechanical things and creates mechanical images in your head, you need to see and understand this. You need to understand this concept very, very clearly. This is the picture you must see. It doesn't matter what you put here. A relay, a solenoid coil, a battery relay. Not a relay, guys. Or not a solenoid, guys. It's a relay, but okay, whatever. It doesn't matter what you put here. An ignition coil, same thing. It doesn't change. Okay? When you put this here, whether we care or not, this magnet inside here is producing a north and south pole, and the flux looks like this. And like I said, for me, it's always green. I don't know why. I just like green when I think of flux fields, because I guess my joke in class was, in the springtime when the snow melts, fields are green, right? You know, those of you who live where there's snow and fields and whatever. But it doesn't apply much in Miami, if you're watching this in Miami. But at any rate, the point is that this is the shape of a magnetic field, and it is absolutely essential that you understand it. Now, I'm going to show it to you in a really, truly, absolutely, truly, truly magnetic field here, and you're going to see what I'm talking about. So hold on. What I've done is I've taken a small bar magnet, and I've taped it to the bottom of piece of paper, cardboard. I got a sheet of paper here. This is a very old tube of the two-part epoxy, you know, the epoxy, whatever, it comes in the plastic tube, and it's like a silly putty or like Play-Doh, and you squeeze it together. All right, well, very, very early on, almost 22, 23 years ago, I went through and I was able to take some brake dust, and I was able to get the brake dust and get the really, really, really fine shavings of brake dust, and I was able to use this, and I still have it. It's the original thing, it's the original tube here. Alright, and what you'll notice is, I hope, is that you'll see, if you look carefully, okay, so I'm making cinnamon toast for my kids here, you don't want to put too much cinnamon on it. Alright, now, I'm looking up here, oh, okay, hold on. Alright, there we go. That's kind of close to centered, I guess. Now, if you notice, the paper's a little coarse, so it's kind of holding the dust there pretty well. But you'll begin to see the shape I drew for you earlier, this magnet isn't perfect, but it's pretty good. You'll see the shape, okay, and you can see these curves, and you can see the straight lines here, and you can see how they're starting to curve. Now, what I'm going to do here, and I hope this works the way I hope it does. Let me do this a little bit more. Okay. Now, you notice what's happening there. Can you see that? You see how that's perfect? I mean, it's perfect, okay? I'm not exactly sure where I got this bar magnet, and it's behaving a little bit differently than I kind of thought it would, but it's still working pretty well. And so if you notice, all of these shavings are moving into a perfect alignment and orientation relative to the poles. All right. So I want you to look at that, okay? And I want you to see that shape, because this is what you have to see. Your mechanical brain has to see this. You don't just look at a magnet and go, ooh la la magnet, blah blah blah. No, you look at this and go, oh look, it's producing a polarity, and this magnetic field looks like, I'm going to drop it, and I don't want to drop it. God bless America. Hold on. Wait, frack. Hold it. Okay. See, I was being stupid now. Okay, there we go. All right. Ooh, that was kind of cool. I was about to demonstrate something, and you'll see very clearly what I'm talking about here. All right. Now, you can look inside a transmission or a differential or a valve spool, and your brain can say, that's what it looks like, and here this thing moves this way, and this gear turns this way, and the rack turns this way, and the pinion turns this way, and blah, blah, blah. Okay, you need to do the exact same thing with this. Okay, do not go to the next video until you have committed this picture to memory. You must see this. This is not optional, because what happens is, as this magnet turns, as those flux lines pass this wire, there's no difference in the angle. So the motion, don't look at this angle, look at it's moving this way. It's turning in a circle. See that circle? Okay. Here, I'll do it this way. All right, wait, I use it. Okay. Now, as this turns, notice that right here, I'm moving in this direction, and the lines and the motion are at 90 degrees. And then I come around here and notice the lines and the motion are at 0 degrees. And then I come around here, but notice I'm moving in a different direction now. I'm not moving up anymore, I'm moving down, alternating directions. So now this is moving in this direction, but it's 90 degrees. And then it comes back to where we started, and now it's moving and it's 0 degrees. So here we have a 90-degree difference between the motion and the flux. Here we have 0-degree difference between the motion and the flux. Here we have another 90-degree between the motion and the flux. And then we come back around here and we have 0 degrees between the motion and the flux. 0, 90, 0, 90, 0, 90, 0, 90, 0, 90. That's how it works. Okay? What does this represent? This means that when the angles between the wires and the magnetic field is 0, we're not cutting any flux lines, 0 voltage. When we're at 90 degrees of rotation, 90-degree angular cutting, we're cutting the maximum number of flux lines, maximum cut, maximum friction, maximum voltage. We keep coming around, 0, 100%, 0, but notice we're in the opposite direction. Look in the book. Four-finger flux. Center finger conductor, thumb is motion. That's the relationship. That's the ratio. If I take this piece of wire and move it in this direction through a magnetic field that looks like that, we get voltage. That is a magnetic field. Please, please, please don't not know that. Now I'm going to try something here. I've got this nut that came off the back of a solenoid, and it's magnetic. Obviously, there's this. By the way, that's why this is called a magnetic pickup, in case you didn't know that. Okay, so what I'm going to do is I'm going to slide this carefully underneath, and they'll do this in a lot of textbooks, and they'll show you if you put a piece of metal, magnets like metal better than they like air. I think that's right. Hold on. That's good. Now, I don't know what's going to happen here, but I hope what's going to happen is you're going to start to see the outline of the nut. Oh, wait a minute. I'm going to change this a little bit. I'm going to move it. Hold it. Yeah, right there. Oh, okay. All right, here we go. Ready? Let's see what happens here. Whoa, 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 whoa. Look right there. Look right there. See, it's changing. That's because the flux is now not flowing through the air. The flux is all flowing through the nut, which proves that magnets like steel and iron better than they like air. That's why the air gap in magnetic pickups is so critically important. This stuff is not mystery. This is not a mystery, guys. This is purely mechanical stuff. So you'll see, you're kind of seeing the nut here. It's not perfect, but it's close. There's the nut right there. Okay? And that's proving that the magnetic field would rather go through the steel than it would go through the air. So the nut is intercepting the flux, and the flux is actually going through the nut and then coming out the other side. Okay? So that proves that flux, whatever the hell flux is, likes metal better than flux likes air. Okay? All right, so that's the first and most critically important video on magnetism, and there will be several more. And I want to make sure you guys watch this video as many times as you need to start trying to understand this relationship between the direction of the lines of flux, okay, very important, the angle of the lines of flux, and the direction of motion. Not this, not the wire, but the direction that the wire is moving, okay? And if you look inside an alternator, if you look inside a generator, you'll see that if this is the rotor like this, then the windings are out here going this way, but it turns this way or this way, but whatever. So the motion is what matters, not the angles of the wires. The angles of the motion is what matters. And that's critically important for you to understand, because when we get back to the sine wave, you're going to understand better why this angle is so critically important and why it affects the output of the genset.